Okay, we'll go ahead and get started. A couple announcements. The course materials are located in Canvas. So a couple things about that. I know you use your phone and your tablets more so than laptops, but when you take exams and submit assignments and stuff for like bonuses or whatever, try to do that on your laptop in a web browser and not through the app. I don't see what you see in Canvas. I have my own sort of instructor view. And so when you have issues about finding stuff, I don't know what you're talking about. And that's generally because you're using the Canvas app. And I use the Canvas app to like grade things, but it's buggy as hell and it rarely works consistently. But if you go on the web browser, there's the Pages thing on the left-hand side with course materials. Click that, it'll launch your e-textbook, which is Organic Chemistry by Wade. There'll be some other online stuff. Anyone ever used Mastering with Pearson before? See some happy smiles in the crowd. Of all the homework systems between Wiley and Pearson and the other vendors, I think Mastering's the best one for chemistry. I'll set some of that stuff up probably later this week or next week. Anything that you see that shows up into Canvas as an assignment is not for points. It's just for you to access the problem sets and crap they have with the book so that you're getting your value of that. So there's, if you launch the course materials, then go into the textbook, you can see all the problems, just like you would in a normal textbook. The other stuff they have is more interactive. So where you're actually clicking and drawing crap. Again, that's just for your own practice. The other electronic required course material is Organic Chemistry as a Second Language. And you'll find that as sort of a separate tab you can click on that will launch this. And then you'll see all this stuff on your tablet. And then I haven't checked it out yet, but hopefully within like these problems, you can like just draw on the page and it's interactive like that. Can't validate that, I haven't tried it, but the reason that this is included as a course material is because it's primarily just problems. I mean, the author gives nice explanations of things, but your success in this course, and ultimately your success is dictated by the final exam. Please read the syllabus and make sure you understand how you're graded in this course. You're essentially just earning points that you fill into grade buckets. So everyone starts at 0 points. You start earning those points into sort of the F bucket, and when that gets filled, it goes into the D, then the C, then so on and so forth. None of your grades are normalized to any other student in this course. So when you all think of, well, he didn't curve this or that, that's really a misunderstanding with a lot of students about what a curve is. A curve is normalizing you to someone else's performance, and it's really not fair to your performance. So you're graded on an absolute point scale for your own effort in performance in the course. So related to that, this is the only hard copy material that's required. It's, again, in the bookstore. It's the ACS study guide. I bought this version because this is the second version that has semesters 1 and 2. So I don't think I really need to create a separate sort of activity list for this. You just open it up, it says semester 2 stuff. That's what you should focus on. And I know December is far away, but take a snapshot of this moment in time, and we will be sitting in here taking the final exam faster than you know it. So start using this like now. And my advice is for to practice for this. Just do 1 or 2 problems from the module that we're on, and then as we do more modules, do a little bit from each, because that's how the final exam is presented to you. There's concepts from every different chapter, and there's no specific order to it. In terms of tracking your grade progress, there's an Excel file that I uploaded, and you can start shoving your points into that as you earn them. How many of you know how to use Excel? So pretty much all of you should know how to use it. You have to download that file and save it on your computer. If you just click on it, Canvas shows it, you can't edit it. But as you put points in, some stuff's going to happen, and then your letter grade will spit out for that point in time in the semester. It's not your absolute letter grade. So only as you populate those boxes will you start seeing your grade trajectory towards the end. I mean, you can go in there and put numbers in, what you think you're going to score, and sort of model out what your grade will be. The other caveat to that is I'll upload different versions of that Excel file as I offer you bonus opportunities. So again, because I don't curve anything, you're getting your curve through participation in the bonus stuff, which is like little crumbs that I'm throwing out to help you prop up your scores going into the final. And those things shouldn't take you terribly long to do. It's not like some 15-page paper with 30 references or anything. So there's a couple of them in there now regarding the ZipGrade stuff to make sure that you can access your ZipGrade account. Your module exams, which are online, are through ZipGrade. And please, pretty please, take those on a laptop in a web browser. If you try to do it on your phone or your tablet, I think you're going to run into some issues with just being able to read the exam and seeing what structures are. You don't want to be pinching and zooming things, because then that's just going to take time and distract you. I think that's pretty much it. Any questions you have about course policies or mechanics of the class or anything? Alrighty. So we got to get through this stuff, which is 1.2, 1.4 editions, and then Monday we're going to start talking about how conjugation affects color. And then I'll open up another little bonus for you in Canvas. Looking at this water bottle. What color is that water bottle? What color would you say that
This
water?
one?
Yeah.
Purple, pink.
Purple. Anyone have any fancier names for that color? Magenta. Fuchsia. I was thinking fuchsia. So the connection of what we're studying in sort of real life is, if I could just ask you a question, why did you buy that water bottle?
Because my favorite color is purple.
So there's this psychological, emotional sort of attachment we have to color. And the company achieved its desires in selling you that based on that connection. So again, today's stuff is going to be kind of boring, but when we get into color, you'll understand how the conjugation gives substances the color, and then like, hey, I'm really hot to trot for that water bottle, so I'm going to spend some money and buy it. And that's how science is used to influence you in marketing and advertising. So look for that on Canvas. And the other thing I want to say is I get a lot of emails about this. That's why I created the Excel file. Canvas is not going to calculate your letter grade for you. It just doesn't have capabilities to do functions and predict or model out your letter grade. So anything that's listed as a bonus, those points are not included in your total point score. So Canvas doesn't do that because there's downstream effects. But if you use the Excel file, it will do it for you properly. And so that way you know sort of where you stand in terms of what you want to get out of the course. So today we're going to focus on two reactions of dienes. So di meaning two, ene meaning alkene, and these are the conjugated dienes. So they're very different mechanisms of just mechanistically, and then ultimately the products they produce. So as we said, continuing on from Module 5 of 255 about electrophilic additions. And so we were saying this general reagent, AB, was an electrophile. And then the pi bond was the nucleophile. So, for example, in that electrophile AB, if we were using bromine Br2, A and B would be the same thing. For the case we're studying today, HBr, so that's H and B are different. We have H and then Br. And what we're looking at is how the HBr will add to the diene that's shown. So there's 4 carbons, 1, 2, 3, and 4. 1 and 3 tell you the start of the alkenes. So buta 1,3 diene. So I'm going to generally just call this the nucleophile, and then HBr is the electrophile. Now when we look at the product distribution that's shown, there's 2 types of products formed. The one on the left is called a 1,2 addition. These numbers here are relative numbers. Relative meaning those are where the action's happening. Those numbers are not associated with the formal nomenclature of the product. Even though in this case things match up to be that way, in general it's not. So when I say 1, 2 in the relative sense, and I'll just draw this maybe in blue, this is what we mean by 1, 2. Those 2 elements added right next door to each other. So I'll underline that in blue, and then I'll do this one in green. So 1, 4. That's their relationship to one another. So as a review, and I'll draw the mechanism on the next slide, the electrophile obeys Markovnikov's rule. And that was stating that the electrophile, in this case, the specific element is the H, adds to the carbon of the alkene that has the most hydrogens. So for both of those products, that's position 1. The reason for that is it generates the most stable carbocation. Based on what we know of organic 1, maybe I need to use my hand to do this. if you just had just that, just this alkene, you can see how H and Br add there to give you this. But now, what about here? What is different in this mechanism that allows the bromine to add over here and then see that sigma bond? Why is there now a pi bond between those two carbons? So something unique is happening in the mechanism that's producing two products. And overall, like kinetically, like if we had to write a kinetic equation for this, if we say the starting material is A, that one starting material can go to two different products, B and C. And that's dependent on an intermediate in the mechanism. The other thing that's important here is notice the temperature. So 0 degrees or 40. At 0 degrees, we get about 70% of the 1,2 product and 30% of the 1,4. If we raise the temperature to 40, so we're all familiar with 0 degrees in terms of like water and ice freezing and melting, but do you have any feel of what like 40 degrees is? So what's room temperature? Like what's the temperature in here? About 25. So 40 is 15 degrees Celsius above that, and I think it was like 40 degrees outside. I don't know what the conversion to Fahrenheit is, but that'd be pretty warm, uncomfortable. But overall, from 15 to 40, it's really not that big lab-wise on the temperature scale. But see how the product distribution then changes? The only variable we're acting upon is the heat. So now we have 15 to 85. And so the temperature allows us to sort of manipulate the outcome here. So let's walk through the mechanism to see why things are changing and what are the reasons the distribution flips one way or the other. So we'll do the curved arrow formalism here, and again, that was the curved arrows are showing the movement of electrons. As a review up here in the right, that sort of arrow, so that double-headed arrow, that means two electrons are moving. That's called a polar reaction. Alternatively, but not for this mechanism, if you have one electron, a single electron or a radical, the arrow now is a fishhook. So it's subtle, but that double versus single, so that's two, this means one electron, and that's radical. And so the arrows have to flow in a certain way, and that is really dictated by electronegativity. Our pi bonds of the butadiene are supplying the electrons for the first bond formation. That means that reagent is a nucleophile. So the other thing has to be an electrophile. So we'll take this one kind of slow. I'll give you some gory detail about it, but as we learn more mechanisms, it's going to pick up a little bit more in terms of the pace. So the pi bond has 2 electrons. And how do we know it wants to attack the H of HBr? Well, bromine has 3 lone pairs. So we can say that's delta minus. And therefore, the hydrogen has to be delta plus. So 2 electrons there, that's delta plus. Negative is attracted to positive. So this will flow out like that. And then we know that hydrogen can only form 1 bond, right? So we then have to break a bond. And these arrows flow a certain way. And fortunately for you on the exams, since you're not drawing stuff, all that works on me. You just have to figure out what the right answer is. We want to break that HBr bond, but which way should the arrow go? It has to start at the bond and then point towards the electronegative thing. So that's the correct flow of the arrows. So if I were giving you a short answer exam, I would say a lot of responses would show the second arrow looking like this. Students would do that. And that's wrong because that means those 2 electrons are then going back on that H. And then if you follow that through in the Lewis dot sense, you have a hydrogen with a lone pair of electrons, and then you're going to have some really weird formal charge that results that nature doesn't allow. So just make sure that in terms of the flow, you understand it kind of has to be in that manner. So let's draw the intermediate of that. And since I said it's Markovnikov's rule, carbon 1 is getting the H because then that results in a secondary carbocation. So the carbon is bearing the plus charge. That's the carbocation. The classification is secondary because it has 2 carbons bonded to it. So the other product of this, since we have a plus charge, we need a minus charge somewhere. Since bromine accepted the bonding pair between H and Br, it now has an extra lone pair, so it's formally negative. In mechanisms, we always want to balance out plus and minus. So we started with everything neutral. Everything proposed has to balance out and be neutral. So now the reactivity flips. See, this is negative. So this is now the nucleophile. It's supplying electrons. Carbon is electron deficient. It's an electrophile. So the arrow has to start at a lone pair and then attack the plus charge. And so that's going to lead us to the 1,2 product. That's pretty much what we learned in organic 1, 1,2 electrophilic additions. So how do we propose to get to the other product? Something is happening at this stage right here that will allow us to get to there. And the main concept here is resonance, which we'll talk more in depth in this lecture due to the second type of reaction we're going to learn today. How resonance is important in predicting the outcome of a reaction. So what is resonance? So resonance can occur with plus charges, lone pairs that have minus charges associated with them. And then you also need a double bond. So all of that stuff has to be in a certain arrangement within 3 elements. I'm going to say elements because you can throw in things other than carbon. So we have the plus charge, so carbon 1, 2, and 3. So we have a 3-atom system. You need, again, either plus, a lone pair, or a radical, and then you need a pi bond. So what happens is that structure has a resonance hybrid where the pi bond electrons move. So maybe let me draw this in blue. So the arrow starts at the pi bond, and it then shifts it over to here. And we indicate that with this double-headed arrow. So notice within that 3-atom system, the plus charge moved from, say, position 1 over to the end, position 3. Now, if we classify that, it's still a carbocation. What type of carbocation is it? It's primary. So the carbocation stability trend is tertiary is greater than secondary is greater than primary. So you might ask the question, well, if secondary is more stable than primary, shouldn't it just all flow into the 1,2 addition product? But again, what's unique about this module with conjugation is that pi bond that's there. What you're seeing here, this system is called an allylic system. So it's not only the class, secondary versus primary, it's allylic secondary, allylic primary. The allylic means you have sp2, sp2, that system. The atom next door is the allylic position. The allylic position has, the allylic system has extra stability. And so of the 2 resonance forms that you're seeing, the temperature plays a role in the product distribution, not only because of the resonance hybrids, but also something else about the products themselves. So let's just draw that primary being trapped by bromine, and then we'll look at classifying the products and see what's special about them. One thing I do want to say about resonance hybrids, due to the lack of progress or deficiency in teaching and learning, I have to draw these things as separate. I mean, you see them separated on the board. In the physical reality of how these things exist, it's not like the H adds, then you get this one, and then this thing is floating around separate. A hybrid is just one molecule. What the convention or the drawing is telling you is that the 1 and the 3 positions, you have this positive charge. The sort of density of that positive charge can then be relayed into the carbocation stability. But there are not two separate resonance things floating around. So the bromine traps at either position. Now, why does the temperature change the product distribution? The common theme with both products is that there's still an alkene left. Let's classify those alkenes. So let me highlight. Don't want to use that. So that's the alkene part. The way you classify it is by looking at the number of carbons bonded to it. Of the alkene here, how many other carbon substituents are there? There's 1, so this is mono-substituted. Oh, Jesus. The color's wrong here. And then the 1,4 product is what substitution pattern? What? Di-substituted. So you have mono and di. So from one point in the mechanism, you're evaluating on carbocation stability. And now for the product distribution, you're evaluating on alkene stability. So will this let me erase? We'll see. No, it will not. So maybe I can do it over here, alkene stability. So of your carbon-carbon pi bond, you count the substituents. A tetra-substituted alkene is the most stable. So that's greater than tri, greater than di, greater than mono. So of the two factors that are interconnected in determining the product distribution, at the higher temperature, we've allowed more energy into the system. That allows the more stable alkene to be produced. So the connection between the 1,2 and the 1,4 is this kinetic versus thermodynamic argument. When you don't have enough energy in the system, you get the kinetic product. That's the thing that forms the fastest. At 40 degrees, you have enough energy that's producing the thermodynamic or more stable product. The take-home message of sort of this mechanism, like electrophilic additions with either 1,2 or 1,4. As I said, I would imagine exactly none of you are going to become practicing organic chemists in your life. So how is this relevant for you trudging through the sludge of this semester? As my graduate advisor told me, it's really hard to memorize everything. So instead of trying to do that, look for a pattern. The pattern of all of these reactions is this, that dying pattern. You can start hanging other crap off these positions. The only thing that matters is that dying. So when you see other problems in here or your textbook, the mechanism's proceeding just like this. It's just you have all this extra dressing or stuff around the carbon backbone. So try to identify the patterns so that you don't have to memorize every single starting material known to man. So again, the formation of that carbocation is what sort of dictates the two different paths the mechanism occurs. The carbocation stability trend is also important in evaluating that, but also the class of the product alkenes. So again, as a review or a refresher, you know how these reactive intermediates are presented to you. So carbocation, that's the plus charge. What was the hybridization of a carbocation? The carbon is what hybridization? So it's sp2. So sp2 hybridized carbon means there's three substituents, 3 sigma bonds, then you have this empty p orbital where the plus charge is residing. And another reason why this has to be sp2 is because both of these carbons are also sp2. And so that is what it allows that plus charge to migrate over through resonance. So you'll also want to be able to identify, if you see a carbocation, what is its class? So again, secondary, because we have 1 carbon, 2 carbons. Primary, there's just 1. And the allylic part is due to this double bond. So you'll want to be fluent in recognizing those things. So as I said, this is the form of a reaction from one starting material A that's going to 2 different things, B and C. How does that happen? We need to talk about these reaction coordinates throughout the semester that help us understand the energy requirements. But you can see the starting material A is existing in some energy well. And then the cheap example that's shown here is just it's going to a product B and a product C. So on the x-axis, that's your time coordinate. So once you start adding everything in there, the party starts, the time starts. And then depending upon the heat that's in there, the energy determines which one of these hills the stuff is going to get over. So on the next slide, I'll put some more information. When we're talking about these energy coordinates, we're using this delta G, where G was Gibbs. and the little degree sign. That's standard conditions or normalized, where everything is, for any reaction, the conditions are normalized so that you can compare these numbers. So from our starting material, we're going up this hill. The top of that hill, like the very pinnacle of it, that was called the transition state. So those only exist for a very short amount of time. So say like 10 to the negative 12 seconds. They're very high energy reactive intermediates. You could think of it this way: if you didn't eat breakfast or lunch, you would be high energy because you're hungry and you want to eat something. You want to release that negative energy by being satiated. And so once they get up there, the ball is then going to roll downhill to the products. The little dagger symbol is telling you the energy of activation to get over that hill. And then you can compare these heights of the red and blue arrows. The kinetic product is B. And we can rationalize that by, if kinetic means speed, it's easier to get over the hill with the lowest amount of energy. But the thermodynamic product is C. That was the di-substituted alkene. Because look from where we're starting, that energy. Overall, it's lower from where we started at the starting materials. So the kinetic product, we're traversing a smaller hill, but the thermodynamic product, we're becoming more stable relative to the starting material. So when you see these things, say on your final exam, you'll want to know what the different points are on each curve and the relative relationships of things. Any questions on that? Again, this is the very cheap example because they're never this simple. There's usually a lot of valleys and or mountains or valleys in these things between here and the product. So they can get a little bit more complicated based on the number of intermediates and arrows you're pushing in the mechanism. So I'll formally ask any questions, because we're going to move on to the second type of reaction that's very different now. So again, those dienes with those electrophiles can do 1, 2, or 1, 4, and that's all dictated by kinetics and thermodynamics. The next reaction that we're going to talk about is only a 1, 4 addition. So based on your diene starting material, the new bonds that are forming are only at 1 and 4. So within the realm of organic chemistry, and a common theme this second semester here, because really we're learning about the reactions of functional groups. Those reactions are typically called named reactions. And this named reaction is the Diels-Alder, and those are the people shown there on the slide, cycloaddition. So ultimately what we're doing is we're forming a ring, a very specific size and type of ring. And the point of this reaction is to be able to spot what is the substitution pattern to make that sort of ring. And the resonance is going to play a big part in that, in the outcome of the product distribution. So this reaction is so useful for humans, it was awarded a Nobel Prize. And I state that because the power of it to make rings, a lot of prescription drugs and other chemicals we use have rings in them. And based on your starting materials, you can make some pretty complex stuff really quick. This is the reaction that they studied specifically. They were ultimately trying to do something else that's related to another module in this semester. I won't go too much into that. They were trying to do a different type of reaction, and they found this product. It's like, that's not what we're expecting. And then that led them on this other trail that they investigated, and it turned out to be so useful that they were recognized with a Nobel Prize. So again, I'm not going to show you what they were trying to do, but just what happened. So let me switch over to the highlighter. So in red, you recognize that as the diene, correct? So that's what we're continuing on with. And I'm just going to put some relative numbers here in blue. Blue pen. Jeez Louise. So 1, 2, 3, 4. So that's our conjugated diene. That's sort of what this 4 right here means. And then in green, the 2 is this alkene partner. So of the blue numbers, the 1 and the 4, that's where we're forming the new bonds. That's the 1,4 addition. So let me plug those numbers back into the product. So here was 1 and 2 there. There was the 1, 2, 3, 4. That's how that maps on. So I'll highlight. So those are those 4 carbons. I want this to start looking like unicorn puke here, but I'm going to call that carbon there a yellow dot. That yellow dot ends up right here. So the new bonds that we formed, I'll just highlight them in green. So if we count 4 plus 2, that's 6. And then overall, if you look at the new ring that was formed, it's this ring right here. That's a 6-membered ring. Then if you strip away all the other crap that's bonded there, what ultimately is produced is a cyclohexene. So the product of every Diels-Alder is going to be a cyclohexene. And then all the other stuff that comes along with the starting materials, it's still bonded there. But that's the pattern you're looking for. And based on this benzoquinone starting material, since it has a second alkene, it can do another one, and that's how you get 2 of the Diels-Alder rings in that final product. So I have a little quip here at the bottom. In the strategy of making molecules, organic synthesis, forming carbon-carbon bonds is the most challenging. So the Diels-Alder is allowing you to form 2 new carbon-carbon bonds in a cycloaddition. In, I think, module 4 of this semester, we're going to learn about these intermediates called enolates. And those are important, so important that people have won Nobel Prizes for them as well. Those also form carbon-carbon bonds. So I do want to give you a little bit of history on this, why it's important. When Diels and Alder were studying this, they were expecting a different product. They got this thing that's like, what is this? Like, how does this even form? They didn't know how it formed. And so it wasn't until the 1970s that the 3 people shown on the slide were recognized with a Nobel Prize for, well, actually 2 of them were recognized. Woodward had passed away by this point, but Woodward was important in facilitating the explanation of this. So after Diels and Alder published their work, people didn't know how it happened, and it was generally referred to as a no mechanism reaction, meaning we just don't know. And then Woodward started thinking about the orbitals involved. So remember on Monday when I showed you the bonding and anti-bonding orbitals for like just the single alkene and then the diene, you have these bonding and then anti-bonding. He was able to think, well, of the bonding orbitals that all have electrons, how do those phases or colors match into an anti-bonding orbital? So Fukui and Hoffman were more mathematically inclined to describe this with equations and prove all the complex math that's involved. But for our purposes, it's just going to distill down into resonance. That's how we're going to predict things from this. So this is the first product where we formed that 6-membered ring. Let me highlight that in red. And then all I've done is sort of taken this flat thing and added some perspective to it. So we're just changing our eye how we look at this. This arrow here is a retrosynthesis arrow, and it's meant to show us how these things can combine. So maybe I'll recolor. So sort of that, the red there is the diene, the green there is the alkene, and this is an approach, like a trajectory of how the diene is approaching the alkene, and the dotted red lines are showing you how the 1 and the 4 positions form those new carbon-carbon bonds. Now, the cheap explanation of this as drawn, see the double bond like line? The way to rationalize it is to think of the p orbitals that are involved in those alkenes. So you have 1, 2, 3, 4 electrons, each in a p orbital that makes up the alkenes. They make up a pi cloud. then you have this bonding and anti-bonding match to the phases that allows these to approach one another that way and do the 1,4 addition. So in this course, this sort of mechanism, we're not going to learn how to do 1,2 additions. We're just focusing on 1,4. Let me just throw this out there. If you had 2 alkenes and they reacted with each other, what size ring would they produce? Alkene and alkene, they do a 1,2 addition with each other to produce a ring. Can you visualize what size ring that would be? Be a 4-membered ring. So say you have an alkene, an alkene. It would form a 4-membered ring. And you could rationalize just pushing arrows like that. So our textbook, we're only focused on 1,4. We're not worried about the 1,2 stuff that could happen. So as I said, we want to recognize, given a product or a target, what is the pattern that will tell us we can use a Diels-Alder reaction. So the backbone of that cyclohexene that shows you the red carbons, that comes from the diene. The blue carbons come from the other partner, which is called a dienophile. So phile means lover. So that wants to react with the diene. But ultimately, this is the pattern you're looking for. Whenever you see that cyclohexene, you can dissect it that way. So 4 of those carbons are coming from the diene, 2 are coming from the dienophile. And the reason we're going to use the rest of the 17 minutes here discussing this is when you start hanging stuff off, like substituents off these carbons, it then affects the approach of how these things come together. And ultimately, what is the relationship of the substituents relative to one another? And again, that's all dictated by resonance. So we're going to spend time pushing some resonance arrows to see how do the charges match up in resonance, but ultimately, how are the orbitals dictating this? We're not going to go too much into the orbitals, even though your book probably does. We're just going to consider the charges from resonance. So it's called a cycloaddition. Addition, again, just 1,4 cyclo means, for our purposes, that it's ultimately forming a ring, a cyclic ring. If we had to push the curved arrows, you could see them here. We need 3 of them. So we're forming a carbon-carbon bond. We're breaking a pi bond here that reforms the pi bond in the product. And then this pi bond breaks to form that new carbon-carbon bond at the 4 position. The dotted lines here are just showing you the partial making and breaking in the transition state. And then there's our pattern. So the cyclohexene, and then we can see that's a substituent. As I said, where it gets complicated is when we start hanging stuff off this carbon backbone here, or what that is, we need to be able to predict where does it end up on the ring. One of the requirements for this to happen, the first requirement, you have to have a dyene. If you meet that requirement, then we can go down the flow chart and ask the next question. The dyene has to have a specific geometry. And that's related to these terms here. So we all know what cis and trans mean, but what is the S in front of that? So we have 1, 2, 3, 4. And we said the type of bond between carbons 2 and 3 was sigma, right? So the S just means sigma. Now of the two conformations shown relative to the sigma bond, the one on the left is trans. If we're considering the positions of the alkenes relative to one another. So you have S cis and S trans. So here, the alkenes are opposite. Here, they're on the same side. So for the Diels-Alder, you have to have the S cis conformation. So that's another one of the requirements for this to happen. That should be kind of logical because the way the mechanism occurs, the bonds to the 1 and the 4 position happen simultaneously. So as those things approach, those bonds are forming at the same time. It's not like one forms, then some stuff happens, then the other one. This conformation, even though there's some steric mojo going on here that's not good, allows that to happen. When it's like this, you're extending the distance too far that the transition state can't happen synchronously or at the same time. So even though this is preferred sterically because you're minimizing interactions of these groups, this is the lower populated conformer just based on that, but it's the reactive conformer. So how do we get around that? Well, as a strategy in synthesis and making things, we tether. You can take the terminal carbons that you're interested in them, add a linker or tether and lock it. So cyclic dienes do that. So cyclopenta 1,3-diene, you've locked in the S-cis conformation. This thing cannot do anything to form that S-trans. We'll learn about these type of molecules where we have heteroatoms in the ring. So oxygen, this molecule is called furan. Do you know furan is in corn? Like you can take corn cobs, throw in sulfuric acid and boil it, and furan will come out. So you're eating chemicals is what I'm telling you. You can replace oxygen with sulfur. That's still locking it in. And then this cyclohexadiene will do it as well. And I want to put out the caveat that we talked about this molecule, benzene. Even though this has that substructure of the diene, the presence of that third double bond, benzene will not do a Diels-Alder reaction. But there's another caveat to that where you can get it to happen, but you're doing some Dr. Frankenstein stuff to it so that it no longer really looks like benzene by itself. So my point at the pulpit here, as we dig into this semester in Organic 2, since we're learning a lot of reactions, there's always a lot of subtleties. So just be a good politician. Don't commit to anything. Give yourself some wiggle room to explain the off things that don't obey the main rule. So here's a question. That's a target. We can see the cyclohexene embedded in there, right? Just that general pattern of that product. In terms of predicting what does this come from, if that's the product, what's it's coming from, here's our retrosynthesis arrow. You see the position of the alkene? That means the dissection has to happen there. So that's the diene. And either A or B is the dienophile. Without me saying anything else, which one do you think it is? Why do you say A?
Because it's more reactive. Would it be A because because it's like closer together, it is a smoother transition phase?
So
Is that even relevant?
I'm liking a little bit of both. We need to do another iteration and throw in some fancier words here. They both have an alkene, right? They both have CN groups. How would you describe the relationship of these CN groups in A? So we'll say cis. And then for B, trans. Look at the relationship of the CN groups in the product. Do you remember what this bolded wedge meant? It's coming out towards you. So they're both the same, right? So now does that sort of dial us more into A and explaining that relationship of cis must be maintained in the product, because when the transition state is happening, the geometry must be conserved. This bond can't rotate and then have a cyano group be on the opposite face in the product. So that if B was used as the starting material, the product would be that. One would be a wedge, one would be a dash. So ultimately, what that's telling you is one of the factors of the deal is all they're looking at the relative relationships of the substituents allows you to predict the geometry in the dienophile. And that's where we're talking about cis and trans. Other terms that we'll want to know we'll throw out, although there's some finer level of decision making when using these. So syn or anti. So like in the products, for example, we can call those cyano groups cis, but we could also call them syn. That means same. And then these are trans, we could call them anti. It's just a little more finesse.
Would one of the substituents be able to like rotate or no, since it's a
Like in the dienophile.
Yeah.
So whatever you start with, as I mentioned, that has to be conserved. So if you start with this, it's never going to produce that. because those bonds are forming at the same time between the 1 and the 4 positions. It doesn't allow this middle bond to rotate at all. So here's another one to think about and not, I guess my advice is not get distracted about things that are not involved in forming the cyclohexene. So I'll ask this question first. And again, when I write the module exams, I try to write them under the spirit of how you see things in the final, where there's kind of an answer that, like, that's just wrong. You know, based on what I know, it has to be wrong. And then, you know, getting to the right answer, that requires more of the logic. So within the 4 structures shown, are there 2 that you can eliminate immediately, and what reason would you give? So I heard a couple people overlap with A. What is one of the reasons you would eliminate A? So one of the reasons is, you know, here we're starting with trans. This ends up cis. So there's that mismatch. What's another thing about A that's wrong? And again, this is the subtle part. Yep.
It's missing the first ring.
So it's actually missing 2 carbons. So see these 2 carbons? Again, they're just tethering the diene so it achieves the S-cis conformation. They don't go away. They don't get vaporized or anything. So you have to see them in the product. So A and C don't have that. Even though this relationship here is correct, it's missing the 2 carbons. So now we have B and D. So see these 2 carbons? Those are the blue ones. So they're included. That we can make our decision based on that. And then of those, which one is the correct one?
B.
What?
B.
Okay, B. Yeah, B is in boy. And we see that based on this relationship here. We have 1 ethyl group up, 1 down. So that's anti or trans, where that's conserved. So D is not correct because even though those 2 carbons are there, this relationship is cis or syn. So that's what I mean by there is a lot of subtleties in diagnosing, you know, towards the right answer. Let me see what we have with 1 minute. I think we're fine with the number of lectures for this module, so I don't feel the need to rush anything. What we'll do on Monday is we're going to focus on what I'm going to call polarity matching of the diene with the dienophile. And we have to use resonance. So these are our dienophiles. See, all of them have an alkene. And then what's changing is the thing bonded to it. So we're going to look at the resonance forms of this to see where charges lie. Then we're going to look at the same thing for dienes and see how do we match pluses and minuses to see how the ring forms. So we'll do that on Monday. Then we'll start talking about color and try to access your zip grades so you don't have any issues with that.